I'm going to present to you our emergent abilities of large language models in Mirage. Joint work with my fabulous collaborators, Ryan Schaefer, and our advisor, Sandy Coelho. I'm a grad student here, a PhD student at Stanford. So now that this is the beginning of the talk and you're probably wide awake and paying attention, I will give you the main takeaways so that you can remember clearly what are the main contributions of our work. And if this is the only thing you remember, great, remember this. So these are the main takeaways. Okay, previous work argues that improvements in LLMs capabilities are emergent at scale. We help to clarify and articulate clearly the definition of emergence. Previous work basically claims that emergence is an unpredictable and sharp jump in the test performance. And we show that in maybe emergent abilities are not what they seem. We argued instead that emergent capabilities at scale are predictable and not always sharp. The main thing that we show is that emergent capabilities, this unpredictable sharp jump, is actually a fundamental property of the specific metric being used and not a fundamental property of the model. Therefore, the sharpness is predictable and expected. And in addition, we show that by an interventional approach, by changing the metric, that we can control if it's a sharp or not sharp. And therefore, if we can control this, it's predictable, right? So we're not making a statement about emergent capabilities not explicitly trained for. And also, we're not telling you how to score your models, just to be aware that you, of course, I can't control what you do or what you say. Maybe it's obvious, but that be aware of the trade-offs and be aware of the claims you make. And don't be surprised if you use the harsh metric and you see a jump, basically. Background. So I'll give you some background on emergence in general. So emergence has been around in science for a while. The main idea is that as the complexity of the system increases, new properties manifest that cannot be easily predicted or explained for. Even from a complete quantitative understanding of the system's microscopic details. This is like the physics way to say it. Now I'll translate it to computer science parlance, is that even with the formal specification of the full algorithm, we cannot predict what the algorithm will do a priori. Basically, this is not surprising if you're a computer scientist. You are aware probably of the halting problem. I cannot give you a description of any formal system, and you cannot give me an algorithm that will tell you a priori what it's going to do. So emergence might be a fundamental thing that could happen in nature just because of the nature of formal systems and what it means to write things down, basically. Yeah, so another nice quote for this is that the whole is greater than the sum of its parts. Even when you combine a lot of simple things that you understand, once you put them all together, the whole thing might not behave as you expect. That is the concept of emergence. And in this talk, we will explain actually a scenario that is predictable. So that is because not everything is the halting problem. There are algorithms in a constraint domain that you can look at the equation, it's simple and it behaves the way you would expect it. So now, the specific background for emergence in language models. So this is the typical curve that you will see. For small models, the accuracy is either 0 or very, very low chance. Some sort of what I'm going to call harsh metrics, like accuracy will go through the scoring metrics. But for small models, it's flat, and then suddenly it jumps. So if you were wondering where the 6.7 billion or 7 billion llama models come from, probably from heuristics like this one, from this plot, where they just chose something large enough to the right of 6.7 billion to hope that the models are large enough to have an accuracy that is high. So emergence is this. There's a sudden jump, and we don't know why. So our work is to look at these plots and be like, why is this happening as the models get larger? I'm going to show you some more plots so that you know that it doesn't only happen for arithmetic. It also happens for massive multitask language understanding, MMLU, like a very famous Hugging Face benchmark online, program synthesis. Let me show you another one that is not about arithmetic. We have figure of speech, other types of tasks where the accuracy is basically 0 and then suddenly jumps when the model gets really, really large. The x-axis is on a log plot, so it's increasing quite quickly. This is another paper that is quite famous about emergence. They have lots of tasks where there's flat, then jump, flat, then jump. The jump being sudden and unpredictable is the main thing that people define as emergence in this work. So now let's go in a little bit more detail for this plot and their claims. So their claims from previous work was abilities that are not present in small models, but that are present in large models. 2, they cannot be predicted by simply extrapolating the performance on the small models to predict how good the big models will do. Okay, so that is the previous claims. Now you have the background. Now, what is the motivation? What makes emergent abilities intriguing and possibly dangerous? The sharpness and the unpredictability, basically. If true, many critical research questions arise. For example, what controls abilities that will emerge? When will they emerge? How can we make desirable abilities emerge faster? How can we make undesirable abilities never emerge? But the question that this talk is going to be about is emergent capabilities at scale hypothesis correct? Is this really happening? This is the main question that we'll pursue today. So it starts from an observation that we made. So many emergent abilities seem to appear only under metrics that non-linearly or discontinuously scale the model's per token error rate. For instance, 92% of the emergent abilities on Google's famous Big Bench occur only on one of the two following metrics: multiple choice grade and exact string match. Basically, if the model doesn't believe that the right answer if it doesn't put all the probability mass on the right answer, the model gets 0 score. Similarly, something that I think is more intuitively worse is that if the entire string is not exactly as the output, the model scores 0. So there are very harsh outputs, and maybe you can already see intuitively why small models would score 0 on these tasks, and you wouldn't be able to detect if they're improving, because if the models are small or even just learning at the beginning, of course, they're going to score 0 on this because they'll have one single mistake and then they will be treated as if they got the whole thing wrong. Yeah, so these models using this type of metrics has its drawbacks, which I just articulated. Another one is that it might be very hard to track model development with these because you can't really know if your models are improving because it's very harsh. So that is an advantage of not using metrics like this. And hopefully I can suggest some other ones in the talk. So let's go forward. This raises the specter that emergent abilities might not be due to the fundamental changes in the models with scale, but maybe it's due to the choices in our metrics. Okay, so now I'm going to proceed to explain to you our mathematical model. The mathematical model is important. It puts the groundwork of our work because it basically shows that we can predict this, that this was expected, that these sharp changes are actually a property of the metric being used, and that we can intervene and change it and it goes away. So we can even predict the sharpness. That is basically the main point of this. So to set up the stage, step 1, we first suppose, this is an assumption of the mathematical model. It's based on reality. Scaling laws. Scaling laws are really famous in large language models. There's lots of papers. And basically it says that as the test loss falls with the model scale, i.e. as the model gets bigger, the test loss falls. And in fact, this is such an accepted claim. And we really want to know if this is always true, that Anthropic has a challenge that will give you lots of money if you find the reverse. If you have a model that gets larger with more compute, more data, more parameters, and the loss increases, let me know. We can submit and get lots of money and do lots of cool research. Just kidding. But seriously, the reason this a serious assumption that is widely accepted. Okay, in a log-log plot, it looks like this. As the loss goes down, and as the number of parameters increases. And for concreteness, suppose that the per token cross entropy loss follows a power law as a function of the model size. N is the model size, i.e. the number of parameters. This is a normal a famous power law. This is just a typical power law. So L is just this equation, and that is what it looks like on the log-log plot on the right, just a linear curve. Okay, alternatively, we're going to show you that when we have this assumption, how the accuracy scales, and therefore show you that accuracy intrinsically always has an S shape, a jump. So, okay, this is what we do. We solve for the per token probability of selecting the correct token, i.e. we make the probability, the accuracy, the subject of an equation, and express it as a function of the model size. So this is the equation, high school arithmetic. And then we make the probability of getting it right, the subject, and we have that it's an exponential of the loss, basically. Meaning that now that you see this, you wouldn't be too surprised that if you score your models with an exponential, you would see some sort of very large jump, right? I guess it's sort of immediately obvious that there should be a jump. And in fact, this proposes that this is a fundamental property of the scoring function, even when the length of the string is 1 and not a fundamental property of the model. And here I show you some simulated data. On the left side, we have our assumption, scaling loss. That's basically that the loss is falling down as the number of parameters increases. And therefore, the accuracy based on this equation looks the way on the right. It looks like an S shape. There's a sudden jump. The colors are how it varies as the string length varies. So intuitively, if the length of the string gets longer, you would expect that it's harder to get something right. So it's sharper. And that's what I'm trying to show you here. Yeah, so we only need scaling loss on the left. The right is a sharp S shape. The sharp S is not unpredictable, right? I just showed you a model. I predicted qualitatively that this can happen. And because a lot of plots also are actually sampled sparsely, I just wanted to show you this sparse sampling of one of these S curves. So sometimes you can't even see it if you don't sample it densely enough. Okay, now that we have this, I want to show you how the models, how these plots scale non-linearly as you process the accuracy with different things. So for example, if you change the string length, how things change. So if you choose a metric that is nonlinear and that scales the per token error rate nonlinearly, you get the plot on the right. The blue curve is the mathematical model, and the green curve is the published emergence abilities. Basically, they look the same. The example task is adding 2 k-digit integers. We measure performance with exact string match. So you only get 1 if you get all the digits correctly and 0 otherwise. And now this is the equation. And as you can see, it's exponentiated as the number of tokens increases. Okay, now we're going to intervene and change the scoring function. Once the scoring function changes, we're going to show that those plots change. And therefore, the main thing driving the mechanism driving all of these plots is the scoring function. That is like the main thing I'm going to show in this plot, in this next slide. So now instead of choosing a nonlinear metric, let's choose a linear one. So it scales the per token error rate linearly. This is the plot that you get. Basically, even when the length is 5. So you get something that looks quite linear. Example task, the same thing, arithmetic on 2 k-digit integers. We measure performance now using token edit distance, basically just how many tokens you got wrong. And this is the mathematical model that for token edit distance, which depends on the length string L. Now, to continue this, now we're going to look at a different family of scoring functions, which is discontinuous metrics. That's how we're calling them. Basically, it scales the per token error rate discontinuously. When you discontinuously score the per token error rate, you get this plot. Again, you can see that the published results match qualitatively our mathematical models. And the task again is to choose 1 out of 2 multiple choice options. So basically an SATs like question. This is the scoring function. Again, only give the model credit if it has all the probability on the right answer. Otherwise, don't give it anything. And now that you know this discontinuous scaling, what happens if we intervene and change that metric to something that is continuous? So this is, again, driving the point down that intervening on the metric, if that is an important property that is driving these observed phenomena, then by changing it, the plot should change. So let's change it. Now let's use a continuous scaling. This is how it looks like. And it's the famous Breyer score, again, on multiple choice. And the Breyer score is mean square, basically 1 minus the probability of the correct answer. That's it. It's very simple loss function. It looks linear. So now, to give you all of the previous slides in one place to summarize all our results. So, okay, look at the center, figure A, that summarizes the assumptions that for our mathematical model and reality. Scaling loss are basically, as we know, lots of evidence exists. Then a mathematical model for the probability of getting something right. The accuracy, it's a function of the loss, and it's an exponential. This exponential is what drives the S shape. If you scale that exponential non-linearly or discontinuously, you get the plots on the left. The blue plots are the mathematical models. The green ones are the published results from previous work. And the right ones show that if you ablate, you intervene and change the metric, the plots change to look more linear. And in the future slides, we'll show how that happens on real data too. Awesome. So just to summarize, here we argue that there are no sharp, unpredictable changes in the model's capabilities with scale. The hypothesis is that the performance across scale is attributed to three factors, and we explore them and intervene with them. Using a metric that nonlinearly or discontinuously transforms the per token error rates. That's the hypothesis. The other hypothesis is that we don't have enough test data to accurately estimate the performance of smaller models. So if you only have, like, say, 2 test points, and you try to evaluate if your small model is doing well on 2 test points, it's very likely you'll get everything wrong, basically, with those metrics. And then finally, that evaluating on too few large-scale models doesn't give us the full picture. Okay, cool, interesting hypotheses. But do we have any evidence? That's the question. So we're going to do this. We're going to use OpenAI's InstructGPT, basically GPT 3.5 family, on integer arithmetic tasks and test all of these hypotheses. We're going to do a meta-analysis of the metric of choice and emergent abilities on the big benchmark, because we also want to explore Google's models and their claimed emergent abilities. And finally, we're going to induce emergent abilities on never seen before models, toy network vision models. There isn't that much hype on vision networks being emergent. We're going to start a trend now. No, but more seriously, basically what we're going to show is that something that didn't seem to have emergence, we can induce emergence just by choosing a metric that scales as discontinuously or non-linearly. So now, predictions for InstructGPT on arithmetic tasks. So now we're going to show you the data we're going to continue and show you the data. On the right, these are actually our mathematical model for this task. When the light curve is length 1, the dark curve is length 5. So as it gets darker, the length of the string gets larger. And we show it at the top. This top one is the Levenshtein distance, the token edit distance. So the linear one. And the bottom one is the accuracy. So what we call the harsh one, or the emergent metric. So we show that by changing the metric from sharp to soft, we can change what it looks like emergent to non-emergent by increasing the resolution, i.e. the number of test examples. If we increase the test examples, then we can actually see what the real performance of the small models are. And regardless of the metric, if increasing the target string length should affect the model performance as a function of the length 1 string. So yeah, so those are the 3 things we're going to do. And on the bottom left, again, the assumption. This is our mathematical model. So the light curve is length 1. And as we non-linearly scale we make the string length longer, we can see that it becomes sharper and sharper on our mathematical model. On the right, we can see that although it depends, as the length of the string changes, the slope does change, but it's always linear. It's a linear change in the slope. So left, sharp, because we're using a sharp metric. Right, we're not using a sharp metric, so it looks linear. That is the main thing to remember here. Now let's look how the mathematical model looks in comparison to real experiments on GPT 3.5. This is the performance of two-digit integer multiplication, again, arithmetic tasks. And once you have that, we have on the left, and the accuracy is sharp, and it behaves the way our mathematical model predicted. For the pink, the lighter curves, it looks smoother. And when it becomes when you have a length string of 5, it becomes sharp. If you look at the bottom, we have a flat curve, and then it jumps sharply. But when you change the metric, it becomes soft, implying that the metric is very important to how you produce these plots. This second slide is just reinforcing the previous plot with more data, basically 2 4-digit integer addition. Again, the same point on the left. there's a sharp jump. Look at this dark curve, and the dark jump is removed once we use a token edit distance, something that is soft. Now, that is the main point from these plots. Changing the metric changes the plots. That is the main thing to remember. Now, let's move on to the second prediction, increasing the resolution, a larger test set, basically. Again, the mathematical model, the dark curve looks like a jump. And now, instead of changing the metric to something softer, you can analogously think about it, or intuitively, that the y-axis is changed to a log plot, and we're trying to zoom in what's going on in the flat region for the small models. That is what we're going to do. And this is a mathematical model zooming in on the small scales. So how does this look for real models, basically? So for two-digit integer multiplication, we have this plot. When the model has a small number of parameters, again, as the previous plots, there is a flat line, and then there's the jump. But now, once you zoom in, the model doesn't look like it has zero accuracy. It has this accuracy, which is non-zero. The dotted line is our chance, therefore implying that once you get enough test data, you can actually measure the accuracy properly. So it's really important to have a large test set. And not all the tasks in the previous benchmarks have that. For example, Persian QA, like how many Persian QA questions can you come up with, for example? Now, it's the same, but now on 2 4-digit integer addition. Again, it's flat. And once you have a model that is sufficiently large, there's a jump. The dotted line is the chance. And we can see that the models, even the small ones, do not have zero accuracy. They're not performing at random. This finishes the role of resolution, i.e. the size of the test set, contributing to the apparent emergent abilities of large language models. Now, we're going to proceed to do the meta-analysis of emergent abilities on the big bench tasks, the Google tasks. We also want to see other models, not only OpenAI models. So Big Bench is Google's benchmark suite for large language models. Many language families, Palm, Lambda, Gopher, Chinchilla, display emergent abilities on Big Bench tasks. Hypothesis. So what we're going to consider is the space of triplets, task, metric, model family. And what we're going to look at is if emergent abilities are real, then it shouldn't really matter which metric we use once we analyze the data and try to find relationships. So that is a correlational analysis. Now, an interventional analysis, I don't know what, once we have, if emergent abilities are real, then, and don't actually depend on the metric, then changing the metric shouldn't really change the plots. So that is the main point. So it's like the second point is the same thing as the previous slides, but now with Google data. And it's also important to point out that all of our analysis of the previous plots and the future plots are with fixed data. So we have fixed model outputs. So the models aren't doing anything. They get an input, then they produce an output. The output is fixed, and then we analyze it with different metrics. So the models aren't dynamically doing anything. Yeah, so that is maybe a small detail, but it's interesting and important. Okay, so emergence appears only under specific metric. So this slide is just basically to introduce the notation that Google introduces for what they define as an emergence score. So you have some model X, it's some performance Y, and basically they define an emergence score. So this number is large if it's emergent, and it's slow if it's not emergent. What this number means is it takes the difference between the max and the min, basically saying what is the largest jump relative to the typical jump in accuracy. So it's just like a ratio, how big is it? It's not a definition that I came up with. In fact, this intuitive explanation that I'm giving you is one that I made up last night to see what is a good way to explain where this might have come from. I'm just sort of presenting the data that the metric they used and rationalizing what it might be. It's the ratio of the biggest jump to the typical jump. That is the emergence score. Now that we have that, these are the plots that we produced in the meta-analysis. And interestingly, we have exact string match. We have multiple choice grade. we have the normalized aggregate score, like all of these functions that I've implied in the previous slides as being emergent. They have the largest score according to the score that Google produced. But look at how many others don't have that property. Basically, that is where we looked at this, and this is like, maybe metrics is an important thing to look at. And with this beautiful pie chart, a middle school pie chart, you can see that 90% of the metrics are non-emergent and 10% are emergent. It's just so clear that the metric, there's something going on in the metric. 35 out of the 39 metrics exhibit no emergent abilities. So is this a coincidence? Okay. Well, we'll think about it in a second, but now let's look at this blue pie chart in more detail. From the emergent abilities, which metrics actually produce this jump? What we discover is the multiple choice grade and the exact string match. And this is why we focused on our paper in this talk so much on discontinuous and nonlinear transformations of the scoring, because of this data. Just to remind you, multiple choice grade is you get only a score if your model assigns the highest probability to the right answer. Otherwise, 0. Exact string match, you need to get every token right to get any score. So these are the famous emergent abilities metrics that we discovered. Now let's do the interventional approach. So if emergence is a real phenomena, maybe it should hold for all metrics, right? Like the metric should not really matter. It's like I think it's a reasonable expectation, right? If it's a intrinsic property of the model, it should be present all the time. So this is the data that we analyzed, fixed data from Google models. I believe this is the Lambda model. Probably read the paper for the details, but we have a flat curve. Look at this green one because it's the cleanest one. And then there's a jump. Again, there's like some jump around this line. At this point, sorry, I guess that you can see the mouse, but like in between 10 and 11. And on the second plot on the right, again, there is a jump. On the green plot, you can see the jump at the end. However, when you change the metric, you have smoothly increasing curves. There's no jump at the edge. There's no kinks. And it's especially clear, we believe, in the green one. So that's the one I'm pointing out right now for like pedagogical purposes and presentation purposes. And also it's interesting to look at that these tasks are not arithmetic tasks. So it's not only arithmetic that we're looking at in this analysis. It's important to observe, like if the abilities have been claimed, emergent abilities have been claimed on a diverse set of tasks, let's explore something not beyond just arithmetic. Now, so that is the meta-analysis. Just to conclude it, we did two things. We did a relationship correlational analysis where we just looked at previous work. Then we look at, okay, what type of metric produces these jumps? And then we did an interventional analysis where we actually changed the metric to score the models. And we saw how the jump was present or not present. That is the main two things we showed you in this meta-analysis. Now I will move on to finish our contribution, maybe interesting experiments on vision and inducing emergence and vision. So we have never observed emergence as far as we know on vision. And the way we do it is through metrics again. We made up some metrics and we saw if we can actually induce these jumping curves. So based on what we learned, what do you guess it's going to be? It's going to be something like exact string match. Okay, this is just normal, just mean squared error on reconstruction. So here is CFAR 100. We're doing autoencoding, shallow autoencoders. The parameters are increasing. And we're just doing the test mean square error. Basically, approximately like a continuous version of how many tokens are you getting right? How many pixels are you getting right? Right? It seems pretty intuitive. Okay, now we define this magic reconstruction function with a threshold C. And this threshold C might be why things look unpredictable, because it depends on the C. But what we do is, if you don't have enough pixels with enough mean squared error, then you get no credit. So for each image, is your mean squared error this number or not? If it is, 1 point. If not, 0 points. Once you do that, you get a crazy plot like this one. which is not super surprising, I guess. Well, given all the arguments I've laid out. And I also do want to point out that obviously right now in hindsight, it's sort of obvious, but I don't think any of the claimed abilities were done in like bad faith. I mean, you as a researcher, sometimes you have to abstract things, right? And I do it all the time. I use a black box and I'm like, yeah, let's keep doing the black box. And then that's the beautiful thing about science. We are all a team. We're all working together and we look at things and we talk to each other. That's why I love, what do you call it? Going to conferences. I learned so much. And I think this is what is happening, science. So anyway, for vision, there's more examples in the paper. Also, this is an interesting comment because the GPT-4 tech report actually claims that they have an ability to predict the performance of large models based on small models. So it also implies that even internally, companies might know how to do this. So it might not be too surprising for them to see our paper. It would be my guess. Discussion and limitations of our work. Of course, our work has limitations. No, nothing's perfect. And maybe people in this room will help us make it better. But these are some of the limitations. Most leading LLMs are closed. Our analysis is somewhat restricted by the ability to query large language models. The GPT family provides query access. We didn't even have access to Palm, Lambda, Gopher, Chinchilla. So we can't do a full analysis just because of the economic nature of the tasks, of the models, I suppose. Our mathematical model has an assumption, which is there's an independence assumption, and removing it is quite tricky, but it still was quite useful and produced predictions that seemed true, at least for us. Our analysis does not rule out the possibility of emergent abilities, only that current claims of emergence are not sufficiently supported by evidence. These are the main limitations that I brought up today. And conclusions. So the conclusions are large language models typically improve the scale, i.e. more parameters, more data, more compute. Some have argued that some improvements in the capabilities are unpredictable. And we argue that many claimed emergent capabilities are in fact predictable, as are shown by our mathematical model. And by using alternative metrics or better statistics, you can actually intervene and show that it's predictable. Well, thank you so much for this and hope you enjoyed this. Thank you. Questions? Of course, any question.
There are a couple of things. Broadly, we look at these large language models and try to deploy it on resistance platforms. So one of the key things that will come in is how to quantize these models.
Yeah.
The moment this emergent this phenomena actually appears, essentially we see that some of the weights of the models tend to be, the distribution of the weights tend to be very, very skewed. The sense that there are a whole bunch of weights, they're all in one set, other bunch of weights in another set. So the emergent behavior is of concern in deploying real world device. So what you're suggesting is maybe if we change the metric, this may not be visible as
yeah, I think so. Yeah. Just to repeat the question, just so that I think the microphone is here. So it's that and when we are deploying it on small devices, are the metrics what tells us if those abilities are present or not? Is that more or less the question? Sort of, yeah. Yeah, I guess. So I think, yeah, I think it's tricky to I guess I have like so many thoughts on this question because I've thought about it, but sometimes just to say maybe a point that maybe has been said before is that sometimes the harsh metric is the right metric because that is what you actually care about. So, however, if you use that all the time, you might be hindering yourself in model development. That is what, at least I believe. So if exact string match is what you care about, then you need exact string match, but you don't need it necessarily to develop your model. You can use something else. Does that help? I don't know if I answered the question, but that is more or less what I think I heard.
Actually, so with the moment we fix a metric,
Yeah.
we basically train the model using that metric in a symbolic manner.
Yes,
That
and
leads to the range.
yes, that's, but we don't ever train on exact string match. We train on cross entropy loss. Sorry, is that correct?
Yeah, so again, it's yes and no. There are cases where we don't do that, right? But the what I hear from you is the metric does have a role to play. One.
Yeah, that's
and
true.
if we were to go back to the slide where you were talking about the emergent behavior efficient models.
Yes, this one.
So, so this metric, what you're saying, depending on the threshold, what we're trying to say is that the number of pixels where we can be, our reconstruction is important, or our classification is important. So what we're trying to say is that as a number, as a threshold, we make it tighter and tighter. Unless the model becomes large enough, we are not able to see the model is not narrowly, it's not other capacity or intrinsic capacity or whatever.
Yes.
To identify that.
Yes.
So again, which means we would need larger models. And when we have larger models, we suddenly see that at some thresholds, they start classifying or reconstructing.
Yes, that's true. Yeah. Once the model is large enough, it gets enough of the pixels for this scoring function to assign credit.
Right. So, but then if you look at the large language models and parameter efficient fine-tuning techniques, right? So they do suggest that these are all over parameterized systems, which essentially means that even without it going to such large models, it has some latent capacity to do the, sort of, if trained correctly with the right data, it could achieve a similar performance. So, is there an interplay of the loss function, the data, and the model that comes to fore when we talk about this?
Yes, I do think so. Like, I think like if your data set is too small, you probably won't get a good test error. Yeah. So there is a compute, data, and model size play a crucial role. Yeah. Definitely.
It's fascinating. You'll continue to talk, I think.
Yeah, no worries. Yeah. Yes, Ethan.
Yeah. I want just to make a comment.
Of course.
First of all, wonderful work.
Thank you.
I was looking for the details. I'm going to be less generous than with these companies. They obviously knew that it was going on. I mean, Google and OpenAI, they kind of think, oh, we have the smartest people. There was an exercise on the side of gaslighting. Let's be clear. I think that if I understood correctly, the key insight, because I'm very interested person, is obviously, and this is the perfect example, right? There is in computer vision, MSNE is a standard method. And the reason I know is I did research on reconstruction and you use MSNE, and obviously you would expect if you just consider the total MSNE, you would expect, I mean, I don't know if it is filtering, I don't know, whatever you use essentially is a matrix multiplication problem that you have an image multiplied. The bigger the matrix, and if it is well trained, the more accuracy the prediction will be, and there should be a almost linear behavior. Now, if you cut it with C, obviously there will be a point where your number of parameters will be large enough to cross the A. Voila, I have emergent behavior. And I think that they were doing the same thing.
Yeah.
I'm not. I've been in Silicon Valley for too long.
No worries. Yeah.
I think it's part of their techniques, and I think that they knew all too well that this was going on. I don't think this is, and they would announce it as, oh, here's an emergent behavior when the smart people that they hire, they pretty knew what was going on.
Yeah. Well, yeah. I don't know. Honestly, I guess I don't really know. Yeah. I don't read minds, and yeah, I don't know. I just try to learn and do the best work, and I think like in the end, it doesn't really matter what my argument is. I think what really matters is for the community to look at the data and decide together what's the truth. And that's what we should be doing.
And I have a second question. This is the question that I just came. Are you familiar with this called deep dimension analysis of models?
I haven't done it in a while, but I was a deep learning theoretician.
Okay, here's the parameters. This is the capability, and whether by picking the right metric, you are, I don't know if there is a relationship between this. This is more of a question.
Yeah.
There's an intersection between that work and looking at models from the maximum ability of.
Yeah, great question. I don't know. During my time at CBMN and MIT, I worked with Professor Poggio. I was very fortunate to work under him, and we did have a paper that suggested that if you normalize the networks appropriately to control like the capacity, you would get like different loss functions, and they would fit classical learning theory curves. So there might be a relationship. I can't really connect their work right now off the top of my head, but there might be. I would probably he would know. Yeah, but great question. Yeah. Hopefully this like opens up like a vast amount of theory to explain and understand these models, make them safer, more understandable. Yeah. Any other I think somebody from the chat. Thank you for okay. I'll just read it. Thank you for the presentation. No worries. Yeah, a bit open-ended, but this result give. Oh, sorry. I need to get okay. This result give a hint that learned fluid metrics like in RL, when RL models are scaled, can yield even more interesting emergent properties. I am not familiar with what that means. Okay, learned metrics. I see. Like basically like reward functions, reward models. I think this is actually, it's funny. I think I removed that comment from my slides. Let's see what do I have it on my commentator slides? But let's see, let me explore real quick my slides. Let's see, what did I have? Okay, arguably the best metric depends on human judgment, which may exhibit qualitatively different behaviors. Example, human judgment metric can be thresholded emergent. We are unaware of tools and studies for quantifying human judgment in this way. So I guess like that is like the answer our team had for that type of question. We don't really know, but it's definitely fascinating. I think reward models also might have the capabilities to be smooth, right? No, because at least in my own projects, I have some scorings of some data and it's between 1 and 0. Like you can have a 0.8. So maybe reward functions, because in the end, reward models are sort of capturing an intuitive feeling that we have, right? We look at a text and we're like, yeah, it's high quality, low quality. And that is like the number we're trying to quantify. So quantifying this is hard and we do need data. I would say that it's intuitively, or this is maybe now personal experience, my feelings are like more continuous than sharp. So I would say if I had to conjecture, reward models are continuous. Hopefully, at least from my own experience, my reward model is more continuous. And I can decide, yes, no, at some point if I need to make that decision. But yeah, any other questions? Yeah.
We'll post this, the recording online.
Awesome. Yeah, I will post it too. Well, thank you so much for coming. Thanks for your questions. Yeah, have a great weekend.
Thank you.
No worries. Awesome. I'm gonna end the recording. Thank you.
Yes, I have